Hello, good people. Welcome to video one. This is the second derivative test, and the second derivative test is the partner to the first derivative test. And so in video number one here, I want to remind you what the first derivative test said. So here's the first derivative test. The first derivative test, first of all, make sure you remember that the first derivative test, the purpose of the first derivative test is to find x values of the relative or local extrema. Remember, extrema means maximums and minimums. So relative extrema, relative maximum minimums. Another way to say it is local maximums and minimums. So it's a way to find the x values where the relative maximums and relative minimums occur. So what's the process? 3 steps. Number one, find the critical values. How do we find the critical values? That's where the first derivative is equal to 0 or where the first derivative doesn't exist, right? By the way, we should also check that if the first derivative does not exist, does it exist in the original function? Because if it doesn't exist in the original function, then it can't be a relative maximum anyway. So that's something to think about. Second step, we create a sign chart and we analyze it by looking at the first derivative signs, whether they're positive or negative, and or we can sometimes look at a graph of f prime and we can figure that out. And then step number 3, any critical values where the first derivative changes from negative first derivative values to positive first derivative values, then I know I have a local minimum. Any critical point where the derivative changes from positive to negative, then I know that's a local maximum, right? And so basically, most students think first derivative test, I have to build a sign chart. And so we have to make sure that we realize we need 2 things to be true. We have to be able to find the critical values. The critical values of f. And then the second thing we need to be able to figure out is we need to be able to determine a sign change. In f prime. So I want to clear or maybe reiterate something. We find the critical values of f, right? We're finding the critical values of the function by setting the derivative equal to 0. So the critical values are not I guess points of the original function, but it's where the derivative of the original function is equal to 0. So I need to be able to do that. And I need to be able to determine that there's a sign change in f prime. But there are cases where I don't have enough information to do either one of these 2 things. They don't give me enough information to do that. So it doesn't always work. And so what if it doesn't work? Well, then we're going to rely on the second derivative test. So just to make sure, both the first derivative test, which uses the first derivative, and the second derivative test, which uses the second derivative, both are tests to find relative local extrema. We're still looking for this, right? We can either use the first derivative to find relative extrema, relative maximums and relative minimums, or we can use the second derivative to find relative extrema. And it all comes down to this idea. So we're going to talk about this idea, and then we'll pause, and we'll come back and kind of pull out the big concept. So what do we do if we can't use the first derivative test? Well, there's another method. So let's consider that there's a function, f of x, but we're not given the equation for f of x. However, we do know that f prime of 2 is equal to 0. So what does this tell us about f of x? And what does this not tell us about f of x? So let's look at each case. So I know that f prime of 2 is equal to 0. If f prime of 2 is equal to 0, that means x equals 2 is a critical value. And it's a critical value because the derivative is equal to 0. If the derivative is equal to 0, that means the slope of the tangent line is equal to 0. I could have something that looks like this, right? In this picture, this is f. Now, f can go on and do other things, but at x equals 2, f prime is equal to 0. Would you agree with that? If that's the case, I'm looking at my statement at x equals 2, the original function has a relative minimum. I can see it, and that is definitely true. Or same starting point. I have a point at x equals 2, and I know that f prime of 2 is equal to 0. What else could it look like? Well, it could look like this. And this is the graph of f. And f prime of 2, the slope of the tangent line at 2 is 0. So I could have something like this. If this is true, that means f of x has a relative. Did I put it backwards? I am so sorry. I put it backwards. This is maximum. If you were wondering, maximum, what I was writing and where I was getting that, apparently it's a little late in the day and my brain is not working. Yes, this is definitely a relative minimum. Part A, or case 1, is a relative maximum. Or I could have one more possibility. The third case, I could have something like this, where this is f. And maybe not put the arrows at the end here, but it could have this shape. Oops, it could have this shape at x equals 2. So this is f. The derivative is equal to 0 because at this one point it kind of flattens out. It's supposed to flatten out. And here it has no relative max and min. Are there any other possibilities that could happen if I know that f prime of 2 is equal to 0? Or are these the only things that could happen at that point if I know that at that point the derivative is equal to 0, right? There's only 3 things that can happen. Well, what if we told you that f double prime of 2 is equal to negative 5? What does that mean? Well, from our previous work, we know that the second derivative is related to concavity. And if the second derivative is negative, then I have a concave down situation. And concave down would be a situation like case 1. So if we also knew, we know that f prime of 2 is equal to 0. So we know there's a critical point, and only 3 things can happen. But I also know that the second derivative, which measures concavity, is equal to negative 5. That means it's a negative second derivative. That means that the function is concave down at that point. And if it's concave down, the only possible thing that could be is there is a relative, f has a relative maximum at x equals 2. This is the idea behind the second derivative test for relative maximums. We're relative extrema. We're still looking for relative maxes and mins, but now instead of focusing on the first derivative and slopes for increasing and slopes for decreasing, now we're going to look for concavity. Because if I have a critical point, only 3 things can happen, right? Either I have curvature down, concave down, I have curvature up, concave up, or I have this little wiggle, a point of inflection. Well, if the second derivative I know is negative, then I know I have concave down. It has to be a relative max. Or if my second derivative is positive, I know it's concave up. It has to be a relative min. But if my second derivative is not positive, it's not negative, if it's 0, then I could get something like this, and I don't know what's happening, right? So the moral of the story is we're going to use concavity to determine, as long as I know that I'm starting with a critical number, which is what this was, right? This was a critical number. As long as I know that I'm starting with a critical number, only 3 things can happen, and 2 of those things I can figure out whether I have a relative max and mins just by looking at concavity, which is related to the second derivative. So that's what we're going to establish in the second video, but this is the idea that we're going to use behind it.